All right, but you can see us, right?
I can see you, yes.
Yeah. Okay, good.
Yeah.
So I think let's go just go on. So welcome all and welcome back to this lecture series on deep learning and PDEs. We're very fortunate to have Professor Weinan with us. He has been a pioneer in the field of machine learning and differential equations. He is a professor at Beijing University and Princeton University. And this is the third part of this lecture series. And we're very excited to hear the third part, Professor. So please, the floor is yours.
Thanks very much. I'm sorry that I'm speaking in the dark and wasn't intended, but anyway. So I want to divide this last lecture in two parts. The first part is going to be about algorithms. And second part is going to be about theory, you know, how little sort of theory we have about trying to understand the what's behind these algorithms. Well, let's see. So I'm actually going to start with stochastic control, the control problem, because it's easier to. Why is it blocking me? Okay, good. Okay, so because it's easier to state. So let's look at this deterministic control problem. We have this discrete time dynamical system where X describes the states and A describes the control. A is the control. And we want to choose the control so that the following object is minimized. And this is the usual objective function in control theory, where the first term is the so-called running cost, and the second term is the terminal cost. In the usual formulation of control theory, we're given an initial state, and we solve this problem for that particular initial state. And that's called an open loop control. Now, sometimes we actually look for closed loop control, meaning that we want to look for optimal, optimal strategy, which is described by this function. The control is a function of the state, so that this is optimized for any given initial state. So that's a closed loop control. And in this talk here, we're going to be mostly interested in the closed loop control. And these two problems are very different. In one case, we're just looking for optimal path, a single optimal path coming out of X0. In the second case, we're actually looking for an optimal strategy. It's very different. Okay, now, a very important result in control theory is dynamic programming principle. In order to do that, we define the value function, which is the optimal value given this initial condition, namely at time t, we start at state x, and the optimal value is called the value function as a function of t and x. And by the way, we look here. Big T is fixed. So this is called a finite horizon optimal control problem. Now, obviously, when little t is equal to big T, then this is just the value function is just given by this terminal condition here. And one can show very easily that the value function satisfies this so-called Bellman equation. So this is the Bellman equation. And in principle, we can solve this Bellman equation backwards, and then we will get all the value function. Now, when the state space is finite, this works out very well. Now, when the state space is huge, like in AlphaGo, in the Go game, then this is not so easy to do. And the problem comes, the difficulty is, is the curse of dimensionality. I already mentioned this many times during the past two lectures. Now, okay, so let's look at a concrete problem, concrete example. We just have this linear dynamical system, very simple dynamical system, and the objective function is quadratic. So this is called the linear quadratic optimal control problem. Now, from dynamic programming, we can write down the Bellman equation. In this case, we can solve inductively the Bellman equation, and the optimal strategy would be just this linear function of the state. And the value for optimal value function is just a quadratic function, where the coefficient is given by this recursion relation. So this is easy to solve. In the more general case, we cannot solve the Bellman equation, so we have to do it somewhat differently. And in order to explain the strategy, it's actually easier to introduce the stochastic version of this problem. And you'll see why I prefer stochastic version in a minute. Now, in the stochastic version, by the way, I'm also looking at going back to the general nonlinear control problem now. In the stochastic control problem, we have this noise term here. So this Ct is noise. And again, we have, X is the state at time t, and A is the control. And again, we're looking for a feedback control, and we want to minimize this expected loss or expected cost. Same as before, except that this cost function is taking expectation over the possible realizations of the noise. Now, naturally, we're going to take a neural network approximation for this optimal control, for the feedback control function. And let's think about this in an abstract way. Let's think about this as being some sort of abstract neural network function with the parameters given by theta. Theta t is the parameter that parameterizes the neural network at time t. So this is going to be a one parameter family of neural networks. Now we want to choose these parameters, to optimize this cost function. And then you'll see right away that this problem is very much analogous to supervised learning using ResNets. In ResNets, we had a dynamical system for the states, and that's the analog here. In ResNets, the objective function that we minimize, or in supervised learning, or in all the other learning problems that we introduced in the last lecture, the objective function is always an expectation. So because of that, because the objective function is an expectation, we can apply stochastic gradient descent, very, very naturally. And stochastic gradient descent is very important. As a matter of fact, in real machine learning problems, there's a huge difference between gradient descent and stochastic gradient descent because of the difference in the complexity. Okay, so actually, this is as far as I can tell, this is actually the very first algorithm, deep learning based algorithm for solving problems coming from scientific computing. And it's a joint work with my former student, Jie-Chung Han. Now, if you think about the neural networks, as I said, we have big T number of neural networks. And we just have one objective function to minimize. So from this minimizing this one objective function, we need to find the parameters for all the big T number of neural networks. So pictorially, this looks as follows. So this is the neural network. This is another neural network. This is another neural network. This is another neural. By the way, the S stands for the states. So we have these are all sub networks, and then they sum over in here to give the rise to the total objective function. So we sum over all the neural networks and minimize the total objective function. And that's a composite neural network architecture. And we see this very often in scientific, when we apply machine learning to scientific computing problems. Anyway, now this can be done, this problem can be solved using just standard techniques from supervised learning, as I was suggesting. And here is just one example, which is the optimal strategy for executing a portfolio. And in that case, the objective function is this, P is the price, and AT is how much we sort of sell or buy. And this problem, for some models of the price dynamics, which I'm not writing down the details here, one can solve this problem exactly, and then one can calculate compare the exact solution with the numerical algorithm we just proposed, and you'll see that this is the actual plot of the error as the training goes on. As the iteration in the training, there's different curves stands for different time horizon, and the shaded region is a plot of the variance, the standard deviation that you see when with different realizations of the algorithm, different realization of the noise and different realization of the algorithm. Then you'll see that we have nice convergence, and and we've done many examples of this time. It all look like this. Now, this this story about stochastic control is how we got started about solving high-dimensional scientific computing problems using machine learning-based algorithms. And it's certainly what we're most interested in is solving PDEs. And here we're naturally interested in solving high-dimensional PDEs. And here are some examples of high-dimensional PDEs. The Hamilton-Jacobi-Bellman equation coming from stochastic control or dynamic programming. It looks like this. This is the Hamilton-Jacobi-Bellman equation. The Black-Scholes equation from pricing financial derivatives, or the Schrödinger equation in quantum many-body theory. Now, in these three examples, the last example is quite different from the previous two, in the sense that this is the Schrödinger equation. The Schrödinger equation is, conservative equation, and another important difference is that in quantum mechanics, the wave function is required to satisfy the Pauli exclusion principle. From fermions, this means the wave function needs to be antisymmetric, and that's actually that makes the whole thing very different from the first two examples. So I'm not going to discuss this particular example here. This is a very active field of research. You probably heard about the work from Carrillo and Troyer. This is the paper in 2017 that started using neural networks to solve the quantum many-body problem. In their case, they only look at the spin problem. Spin, that makes the whole thing discrete. So it's actually a discrete problem. And then we look at, together with my former students, we look at the electron problem. So that's really a PDE. And then afterwards, a group from DeepMind developed the so-called FermiNet, which extend the whole thing much further. And then there's also an alternative version called PauliNet. You probably have heard of the story. Right now, it's a little bit up in the air how much one can improve upon, how much one can go with using deep learning-based algorithms for solving quantum many-body problem, the Schrödinger equation. But it's still a very active area of research. So in the following, I'll focus on the first two kinds of equations. These are sort of PDE equations. And as you can see, I wrote the equation in the backward form. The PDEs has one sign. It's got a positive sign here instead of a negative sign. And that's because, in either stochastic control or financial theory about financial derivatives, it's very natural to look at things backwards in time instead of forward in time. Okay, now before I get into the deep learning-based algorithms, let me just give you some overview of prior work about solving PDEs in high dimension. Now for linear PDEs, for linear parabolic PDE, we can write down the solution using Feynman-Katz formula, which I'll explain that in a minute. And then using the Feynman-Katz formula, we can just develop right away Monte Carlo-based algorithms. For semi-linear parabolic PDE, for special forms like cubic nonlinearity or something like that, for special forms of semi-linear parabolic PDE, there some work done by developing branching diffusion processes that models these special nonlinear parabolic equations. Think about KPP, the KPP example. And then Arnold Jensen and his students, and we together developed so-called multi-level Bigot approximation. This is actually a very nice algorithm. And what's nice about it is that one can establish convergence rates for this particular algorithm. Now in practice, it works reasonably well for a short time. But then for a long time, we had difficulties to make it work. To make the error seemed to increase for a long time. But Arnold just told me that he has also fixed that problem. So it seems that multi-level Bigard is also a robust algorithm for solving high-dimensional nonlinear PDEs. Now, for special forms of Hamilton-Jacobi equation, one can write down the Hopf formula for the solution, and then one can develop fast algorithms based on Hopf formula. There's a review article written by Jiechun Han and Arnold Jensen about solving nonlinear high-dimensional PDEs. And I think if anybody is interested in solving nonlinear high-dimensional PDEs, this review article is a nice source of information. Okay, now for linear PDEs, as I just mentioned, one can write down, so this is the linear PDE with a terminal boundary condition, and then associated with this linear PDE is an underlying diffusion process. The Fokker-Planck equation for this underlying diffusion process is very much related to this linear PDE. As a matter of fact, if you take the F away, this would be the Fokker-Planck equation. This would be the Fokker-Planck equation. Now, with the term F, by the Ito formula, one can show very simply that the solutions of that PDE satisfies this integral equation. Okay? And from which, if you take expectations on both sides, this bad term disappears, and this is nothing but the Feynman-Katz formula. And then you can just use Monte Carlo to compute the solution using this Feynman-Katz formula. So solving PDEs becomes computing integrals. And that's always a good thing to do. I mean, in the last lectures, we could kind of sort of explain that machine learning, in a way, it's about converting function approximation problems into integration problems, in a way. Now, what about nonlinear PDEs? So take this semi-linear parabolic PDE where we have a nonlinear term like this here. Now, again, we can write down the underlying diffusion process. This part doesn't involve any nonlinearity, and it corresponds to this diffusion process. And again, using Ito's formula, Ito's lemma, we can show that the solutions of the PDE satisfies this relation and involving the stochastic integrals. Okay, now one can develop this further by introducing something called backward BSDE. The BSDE stands for backward stochastic differential equation. This is a very important tool developed by Padu and Penn. In particular, they were able to show that there's a nonlinear version of the Feynman-Katz formula for the solutions of the PDE. Now, I'm going to discuss that in a minute. But before I do that, let me explain the BSDE here. So if you look at this is the system. Well, the first equation is the diffusion process that we just described. Just take a look at the second equation. The second equation is called backwards. You can see that it's integrating backwards. And then the x is given by the first equation. And here we have y. Y is an unknown. And z is also an unknown. So for this equation, you've got one equation, but two unknowns. What's remarkable is that Padu and Penn proved that this equation has a unique adapted solution. In some sense, you can think of this z as being a Lagrange multiplier for the constraint that the process is adapted. And I think this is a very remarkable result. And this is also related to the Pontryagin maximum principle for stochastic control. And you can also think of this as being the method of characteristics for nonlinear parabolic PDEs. Now, with this tool, one can show that the solution of that there's a very nice connection between this BSDE and this PDE here. And the connection is given as follows. And this is what we call the nonlinear Feynman-Katz formula. Now, as I said, that the BSDE has a unique solution. And that solution is given by the solution of the PDE. And y is just the value of u evaluated at the process x. And z is this Lagrange multiplier term, and which is given by the gradients. In other words, if we think about this following variational problem, stochastic optimization problem, namely we're minimizing the expected difference between the terminal condition and the solution Y of the BSD subject to the BSD, then the solution of this problem is given uniquely by the solution of the PDE. Okay, so here there are several claims here. First of all, that the PDE solution, it gives the minimizer of this problem, of this variational problem. Secondly, the minimizer is unique, that's given by the BSD theory. And secondly, thirdly, 1 and 2 implies that the minimizer is exactly the solution of the PDE. And then based on this, one can also show that proximate minimizers is also a proximate solution to the PDE. And this is proved by my former student, Jechun Han, and my current student, Long. So this is going to be our starting point for developing machine learning-based algorithms. In order to do that, well, we first discretize in time. We're going to discretize these stochastic processes, but the neural, I should explain first, what are the neural networks? Well, first, there's a neural network that defines this mapping. And secondly, for each time t, there's going to be a neural network that defines this mapping. Of course, we're going to discretize in time, as I said right here. So therefore, we're just interested in this mapping at discrete times, at these discrete times. Okay, now, oh, by the way, actually, if you look at this is very much like the stochastic control problem we had earlier. We are minimizing some expectation and subject to some dynamical system kind of constraints. So very easily we kind of sort of adapt the algorithm that we had earlier for stochastic control into this current setting. And you'll see deterministic control is kind of less natural in a way. So that's why we choose stochastic control to start with. But I'll mention the development of deterministic control later. Okay, so this is very much the same as the algorithms we had earlier for stochastic control. We discretize in time, and then we use neural networks to represent these guys. These are very much like the A's we had earlier, and we also represent this mapping by a neural network. And together, we have very similar kind of architecture, and we have a neural network here, and we have the subneural network correspond to each discrete time. And then we have one total cost function. These y's sum up. We can sum up all the y's and then compare the y's with the terminal condition and try to minimize the difference between the two. And that way, that's how we train these neural networks to find the parameters of these neural networks. And it works out quite nicely, as a matter of fact. Okay, so that's what I just said, as a matter of fact. And we call this deep BSD method because it's very much based on BSD. And Jechun has actually developed an open source platform where he put all the codes for people to play with. And as a matter of fact, a lot of people do play with these codes and try to improve upon these codes. And a lot of subsequent work has been done on this subject. Now let's see how things work out in practice. Give an example, simple linear quadratic example. It's called, this is the continuous version of the linear quadratic example I had earlier, except now not only is this continuous in time, but it's also stochastic. This is the white noise. So this is called linear quadratic Gaussian control problem. And lambda is some parameter here. And we take this as our objective function. The Hamilton-Jacobi-Bellman equation in this case, can be written down very simply, and it's this. And in one dimension, if you think about one dimension, this is the canonical Hamilton-Jacobi equation that we have studied a lot in PDEs. As a matter of fact, one can perform a Hopf-Kohl transformation and make this into a linear PDE and solve the and write down the solution for this Hamilton-Jacobi equation. And the same trick, the Hopf-Kohl transformation, can be applied to this high-dimensional version of the Hamilton-Jacobi equation. And then you can write down the solution and use the solution, use the exact solution. Well, this exact solution is also expressed as the expectation. Use the exact solution to calibrate the result of the deep BSD method. And that's shown in the right figure. This is just plot of the solution at a particular time, u at 0, at this particular time, t at 0, x at 0, and as a function of lambda, the parameter here. And you can see the Monte Carlo solution and the deep BSD solution are quite close. Now, one thing that we don't like about these algorithms, I should tell you right away, is that it's very hard to come up with sort of convergence. It's not like finite elements that if you refine the grid and the error reduces by a factor of 4 or something like that, second order method or something. In this case, it's not like that. And there are many reasons for that. We can discuss that later. But that's the situation right now. It's difficult to sort of do systematic convergence study and try to extract a convergence rate. Okay, now there is actually a much simpler idea. The deep BSD algorithm is a rather complicated idea because we had to go through this BSD formalism, BSD machinery, nonlinear Feynman cats and stuff like that. There's actually a much more straightforward idea, and it's just this. If you want to solve this PDE, let's write down this PDE in this form. All the PDEs we've discussed so far can all be written like this. And then this is the boundary condition. Okay, in order to solve that PDE, all you have to do is to try to model U by some neural network, never mind what neural network, some neural network expressed as this, and then minimize this objective function. So we just take this guy squared and then this guy squared. Okay, so this is the least square method. And this is the most obvious idea. As a matter of fact, this is also the first idea we thought about, but we kind of didn't pursue this because we thought it's always important to explore the mathematical structure. That's why we actually did the BSD. But if you compare the accuracy of this thing, and with the BSD, you can see that the BSD method is indeed more accurate with the same number of parameters, reasonably same number of parameters. Okay, but this is actually a much more subtle issue, as I'm going to comment on in a minute. Shall we just do this? Almost a sort of a foolproof kind of approach, or shall we do a deep BSD kind of approach, which is, uses the more mathematical structure, but it also says that it's more special. So you can do this for any PDE, whereas the deep BSD requires some sort of mathematical structure, and then it's more limited in a way. So I'm going to come back to that later, in a minute. Well, actually, I'm going to do that now. So before I finish this part, let me give you a brief literature review about solving PDEs using neural networks, because there's a lot of work right now on this subject. A lot of people are doing this sort of thing. So this literature review is not going to be exhaustive. It's not to cover everything, but I want to make some mention the most important points. First of all, it's an old idea. It's an old idea to use neural networks to solve PDEs. because you can just think of it as a nonlinear finite element method, nonlinear Galerkin method, and you replace finite elements by neural network functions. So people have tried that long time ago. And it didn't, I would say, it wasn't clear that it is really advantageous for a long time. That's why it's sort of not pursued very much later. And we decided, when I thought about, when Jie-Chung Han and I thought about this problem back in 2015, we saw the possibility that deep learning can help us to solve high dimensional problems. And we want to think about, and we asked ourselves, what would be a good starting point? And we decided high dimension is the way to go, because the neural network shows a lot of advantage in high dimensional problems. And we chose stochastic control as the starting point, as I've already explained. And later on, 2019, there's a very nice paper published by a group of authors where they developed deep learning based algorithms for deterministic control. So right now, there's lots of other work about solving deterministic control and stochastic control problems using deep learning based algorithms. But I would say these two papers are the most sort of the representative papers, one for stochastic control, one for deterministic control. Now for high dimensional PDEs, I already mentioned the deep BSDE method. It's described in these two papers. Now, in 2017, there's another important piece of work that I think explored the real advantage of deep learning. That is, try to solve parameterized PDEs, say with random coefficients. Say you want to solve Schrödinger equation with a random potential, or you want to solve the homogenization problem with a random coefficient. And you can try to parameterize the solution with the random coefficients. And that's a very nice paper by Ku and Liu, Jianfeng Liu, and Lexing In. And I think this is a very important piece of work. And then subsequently, there are papers written about analysis of these kind of ideas. Now, in 2017, there's also a paper published called a deep Galerkin method. And it's also about solving high dimensional PDEs, sort of motivated by our work. Now, the deep Galerkin method, really it's a least square method. So the basic idea is very much like this. It's a very much a least square method. So it's not really a Galerkin method, but it's the paper, the title of the paper is called Deep Galerkin method. And that's also an important contribution. Now, motivated by this paper, because I was kind of a little bit annoyed that the name was wrong, should have been called Deep Least Square method. I wanted to develop a real Deep Galerkin method. Remember Galerkin method, if I understand correctly, the Galerkin idea is that you use test functions. That, there's a trial function, there's a test function, you use a weak form of the PDE. That's Galerkin. Whereas Ritz method is a variational formulation. And least square is what I just said. So Ritz, Galerkin, and least square, these are the three most important formulations of trying to solve PDEs. And if you're familiar with the numerical PDE literature, and you would know that we first prefer the Ritz formulation. If there's a variational formulation, that's what we prefer most of the time. And then the least square formulation is kind of the last resort. If we cannot do anything, if we cannot do Ritz, like we cannot do Galerkin, then we do least square. And that's because, first of all, least square usually gives rise to a much worse algebraic problem to solve. And also, it's less accurate and it requires more derivatives. But, if you have run out of options, you always use least square. And but most of the time we were asking ourselves the question, how can we do without using least square? Can we do something better? That's what the PDE community, numerical PDE community, has been trying to do. Anyway, so we were motivated by this deep Galerkin method. We want to develop a real deep Galerkin method. And in order to do that, we first did the rich method, and that's in this paper. But I have to confess that we didn't succeed in writing down the paper that we really want to write, namely the deep Galerkin method paper. So even at this point, how can we develop machine learning based algorithms using the weak formulation is to a large extent still an open problem. There's an attempt published in this paper, but if you look at the thing, in the end, they sort of give up the weak formulation. They still sort of, resorted to a variational formulation, not the weak formulation. Now, it seems to me that the most popular idea for neural network-based algorithms for solving PDEs is this thing called physics-informed neural networks, and PIN. As far as I can tell, there doesn't seem to be much difference between PIN and the deep Galerkin. They all do this. They all do this. So as I said, this is a foolproof kind of an idea. But these guys succeeded in popularizing this physics-informed neural network much better than anybody else can imagine. So this is actually the most popular idea right now, as far as I can tell. But I have to say that, okay, there's one important difference between this and this. These guys, in this paper, they were emphasizing solving high-dimensional PDEs. And this paper is actually advertising using neural network for solving low-dimensional PDEs, like Navier-Stokes or Burger's equation, that sort of thing. And I have to, we're going to discuss that in a minute. It's not really clear what the advantage would be if you want to use this to solve Navier-Stokes equation. It's not clear. Certainly, there's lots of disadvantage. But there are advantages. I'll come back to that. Now, there's another important idea, which is to represent solutions of PDEs as neural networks. So this is the neural operator idea. This is one of the representative papers. And that's also an important development. In my view, this is quite related to this paper here, because this paper is also sort of parameterizing solutions of PDEs using neural networks. Now, besides PDEs, there's also quite some development in game theory, particularly mean field games, work done by Jiechun Han and Hu. And then there's also a nice paper by Risotto, Sanosha, and collaborators about solving mean field games using neural network-based ideas. As a matter of fact, high-dimensional mean field games. So again, the review article gives you a nice overview of this. Now, summarize. Here's my personal view. This is very personal, and might be very biased too. This is what I think the real advantage. These are the situations that I think machine learning-based algorithms would have an advantage over traditional algorithms when it comes down to solve PDEs. Certainly high dimension, because traditional algorithms just don't work in high dimension. So here, it's either machine learning based or multi-level big R or something like that, or write down the solution and use multi-calorie evaluative formula. Now, solving parameterized problem or represent a solution operator or some physical quantities you're interested in terms of the solution, such as the flux, for example, the total flux of a flow, and that's sort of an integral over some quantity related to the solution. So in that situation, we can represent these kind of physical quantities using neural networks, and then you can use that to solve a control problem or inverse problem or optimization problem. So here, in this situation, certainly neural networks has lots of advantage. And third advantage, this is the reason I think that PIN is very popular, is that it's actually a very nice toy. And particularly for introducing applied math people to the world of machine learning, because applied math people like PDEs. And these, ping is very easy and quick. It's a very easy, quick, and rough approximation. Ping provides a very easy, a very quick, even though it might be very rough approximate solution, and doesn't require a lot of coding. That's very important because there's a lot of machinery developed around Python or deep learning like TensorFlow, PyTorch, lots of machinery. So writing codes is extremely simple, particularly if you have a bad PDE problem with bad boundary, bad geometry, or bad coefficients and stuff like that. Then ping is very nice because it's easy and quick, and it gives you a rough approximate solution. And maybe in those cases, you don't want to do a very detailed solution. So this is what I think. These situations, machine learning based algorithms show some advantage. Okay, so this is the first part of my lecture, and I want to go to the second part, which is about theory. I'll close this. Now, there's not very much we have about theory, but I'll tell you how much we know about theory. So I asked two questions. First of all, the new regularity theory for PDEs motivated by machine learning based algorithms. The fact that we're solving these PDEs very high dimension, what kind of regularity theory is needed, is called for. And secondly, error analysis. As I'm going to warn you right away that we don't know very much, but I'll tell you what do we know at this point. The fact that we can solve these very high dimensional PDEs, hundreds of thousands or even more high dimensional PDEs, means that the solution of these PDEs cannot be very complicated. It must have low complexity, even though there are functions in high dimension. The question is, how can we characterize this low complexity? Well, the intuitive answer is that, well, they have low complexity because they can be approximated easily. But the question is, how do we quantify this? From the classical way to do this is that we have some regularity theory. Regularity is a measure of the complexity in approximating target functions using things like piecewise polynomials. We have this kind of a result, namely a function can be approximated by piecewise polynomials. The convergence rate of this approximation depends very much on the regularity of the underlying target function. So this is the classical approximation theory. Unfortunately, as we said earlier, classical approximation theory suffers from curse of dimensionality. Now, it's not just that. There are increasing evidence that Sobolev or Besov or Lipschitz or C alpha, these kinds of spaces, function spaces, are no longer good measures of complexity of functions in high dimension, because these function classes are too large. In high dimension, I would say C2 and C3 doesn't make much of a difference. And I might even want to say that difference in differential equations doesn't make much of a difference. It makes a huge difference in low dimension, whether we're dealing with difference equation or differential equation. But in high dimension, it's not the case. It's something else. Now, the new approach would suggest the following. We have some new approximation theory, as I suggested in the first lecture, and then we try to develop some new regularity theory for PDEs. So the approximation theory looks like this. This is what we saw in the first lecture. And here, these guys replaces the Sobolev norms. And we saw some examples of these pseudo norms in the first lecture. The question is, for the regularity theory, is the following. For the solutions for PDEs we're interested in, are these quantities finite? Do they belong to the right function space? Do the solutions of these PDEs belong to the right function space? One particular example of function space is the Barron space. Let's recall the notion of the Barron space. Now here, we're interested in functions that admit this kind of representation. Namely, it can be written as an expectation over in some parameter space of a function of this form, of the single neuron. This is the single neuron form, and rho is some probability distribution. And we define this kind of a barren norm. Okay, that's barren space. Now we also saw another notion called, this is a notion defined by Barron. By the way, this is what we define this, but the thing that Barron defined was really something like this. And we call this spectral barren space. And we saw that the barren norm is bounded by the spectral barren norm. This is the second kind of a space that we introduced. Now, similarly, there were sort of similar notions for ResNets. It's called a flow-induced space. And for multilayer neural networks, even though I didn't talk about this at all, there's also some notions of multilayer spaces that we introduced. And all these spaces, for functions in these spaces, these kinds of results, maybe not exactly this form, but these kinds of results where the exponent does not depend on dimension, holds. For example, there's three-layer neural networks, there's a three-layer space. For four-layer neural networks, there's a four-layer space. That's introduced in this paper here. So can we develop a regularity theory for this kind of function spaces? Now here are some very elementary results. Suppose we want to solve this equation, okay, in whole space. Then you can write, because this lambda comes very convenient because the solution for in the whole space decays very nicely with lambda, and then you can prove that the barren norm of the solution is bounded by the barren norm of the right-hand side. Okay, as a matter of fact, for ReLU, we can even we can prove something like this. Oh, this result holds if the activation function has finite limits at plus and minus infinity, so sigmoid type. And for ReLU, this is replaced by this. Okay, this you can prove by just write down the fundamental solution, things like that, and calculating. And for the solution of the heat equation, we can write the solution in terms of homogeneous part and inhomogeneous part. For the homogeneous part, we can prove this bounds that the barren norm in space-time is bounded by the barren norm of the initial condition. And for the inhomogeneous part, we can also prove some similar kind of bounds. And again, you can do this by write down the solution and do it. And this is the nonlinear, this is the Hammond-Jacobi equation. For the nonlinear Hammond-Jacobi equation, we can prove the following, that suppose that the initial condition is bounded and it's a barren function and it's bounded from below by beta minus and from above by beta plus. Then we were not able to show that the solution belongs to the barren space, even though the initial condition is in the barren space. But we were able to show that the solution is in the three-layer function space, and with this estimate. So this suggests that even though the initial condition can be approximated very well by two-layer neural networks, the solution, if you want to approximate the solution, you have to do three-layer neural networks. There's also a counterexample. Well, there's the counterexample on finite domain. So if we consider this PDE and a finite ball with this boundary condition, where sigma is just a ReLU, then one can show that the solution is not in the barren space of the unit ball. And this can be proved by looking at the structural theorem for barren functions. And the structural theorem says, structural theorem is proved by Stefan Wojciechowski and myself. It says that barren functions are Lipschitz continuous, and the set on which this Lipschitz function fails to be differentiable is called the singular set. Let's define that to be the singular set. And the singular set of a barren function is of this form. It's a countable union of it's a countable sum of functions whose singular sets are affine subspaces. So the singular sets are, unions of affine subspaces. And from this, one can show right away that this function is not barren function because the singular set is the unit ball. Sorry, the unit sphere. The unit sphere is not a countable union of affine subspaces. So this function, the distance to unit sphere, cannot be a barren function. And similarly, one can show that these guys' solutions cannot be barren function. So these are all we know, I think, all we know about the barren space. For the spectral barren space, there's some sort of recent work done by Jianfeng Lu and his collaborators. And here we're considering a finite domain and using Fourier, sort of a Fourier series representation. So we write this function as a Fourier series, and then the coefficients, from the coefficient, we can define these kinds of norms, which are like analog of barren norm. So barren norm would be continuous version of this with S equal to 1 or 2. And here we can define general sort of spectral barren space with general S values of S. And this will be a discrete version. And this will be the barren spectral barren norm, S order spectral barren norm. As I just said, that's a continuous discrete version of these kinds of things. One can prove the following, that if you consider solutions of this elliptic equation, sort of static Schrödinger equation, then you have this kind of a regularity that, that the S plus 2, the spectral norm of S plus 2 order is, for the solutions, bounded by the spectral barren norm of S's order. So this is kind of a standard regularity result one saw, the sort of regularity result that we saw in standard elliptic PDEs. And here you can show similar kind of results. It's not clear to me that actually these makes a lot of difference because different orders of S may not make such a big difference when it comes to the actual for some reason there's a one page missing. I don't understand why. So anyway, there's a second result also proved by Jianfeng Lu that shows the convergence rate of neural network based algorithms for solving these kind of PDEs. And somehow the one slide is missing. I don't understand why. This is strange. Okay, anyway. Anyway, this is the numerical result that compares the convergence rate that they established with what's happening in practice. And you can see that agrees reasonably well. And that's essentially all we know about theory. And I think it's safe to say that there's lots of open questions in theory and in algorithms, and there's certainly a lot of room for further work. And so this completes my lectures. I think I want to just make one remark. I think in the end, what we're trying to do is to develop some sort of high-dimensional analysis, high-dimensional approximation theory for functions, high-dimensional theory for probability distributions, PDEs, and stuff like that. So at the end of the day, what we're really trying to do is to push for high-dimensional analysis. I didn't talk about dynamical systems. There's also a nice story and certainly lots of open questions about approximating high-dimensional dynamical systems using machine learning. If you're interested in that, you can look at the work of Chen Xiao Li in National Singapore University. Okay, so I want to end my lectures here, and thank you very much for your attention, for your patience.
Thank you very, very much, Professor, for a really, really interesting series of talks. I think we should start with questions here from the audience. Any questions?
I have perhaps a naive question about the first part of your lecture. So, I mean, for what I understood, you solved basically the Hamilton-Jacobian-Bellman equation using some sort of the underlying variational structure of the equation. So, is it somehow a general? I mean, the naive way of thinking would be, so take any equation that is the Euler-Lagrange equation of some variational problem. Can you perhaps construct like a good numerical algorithm using neural network that use this variational structure?
First of all, the deep BSD method does not make use of any variational structure. The control problem certainly makes a lot of use of the variational structure, but the deep BSD method does not use the variational structure. There's no underlying variational structure. It's a general parabolic equation. One can say that one can sort of say that I sort of cooked up a variational structure for this correspondence here, this equivalence here. You can say that, well, this is a variational structure because I've turned the PDE problem into a minimization problem. You can sort of say that, but this is not like the natural variational structure one would, that one usually think about. Secondly, for general Euler-Lagrange equation, when you talk about Euler-Lagrange, there is an underlying variational problem. And for that, the deep bridge method should work very well, usually, except for situations for which, like quantum many-body problem, for which you have to have anti-symmetry and stuff like that. That's complicated. But if you have, the usual variational problem without much of a fuss, now even for bosons, for fermions bad, but for bosons, not a problem. The bridge method, deep bridge method, or many other things work very well.
I see. Thank you. Yeah, that's clear. Yes.
Thanks.
Stuart, you have questions?
Yes, I have a few. I don't know how many you will allow me.
Go for it. Go for it.
The first one, when you compared the PSDE formulation with the strong formulation, numerically, the strong formulation was not performing that well. I was wondering, am I correct in thinking that the BSD formulation is in some sense a weak formulation? Or is it not correct?
What formulation?
That it's a weak formulation, perhaps in some sense, or am I not correct in thinking that?
Well, I don't know what you mean by that. I mean, the weak formulation, I would imagine, would be like lucky. You have a test function, right? Usually, a weak formulation says that there's a trial function, there's a trial space and a test space, and then you have test function. That's usual. That's the usual weak formulation. Certainly, deep BSD is not like that. As a matter of fact, as I remarked, that so far we don't have a robust sort of machine learning based algorithm that based on the weak formulation. I made a try, haven't succeeded yet.
Yeah. What I meant by weak, I meant that the regularity of the solutions that the BSD formulation admits, is it the same as for the strong formulation, or is it smaller?
Well, here you can see why it requires second derivative. That's bad, right? If you look at the BSD, it doesn't have second derivatives. So in that sense, yes. So it's harder to do. I mean, if you cannot do, for example, you cannot use ReLU because the second derivative doesn't exist. So in that sense, yes, it requires more regularity and requires.
And can the discrepancy in the performance be due to the fact that the equation does not have a regular enough solution, that when you require one derivative?
Not necessarily. This is kind of discrepancy also shows up if you solve usual PDEs, say elliptic equations, and Poisson equations using the Ritz formulation or the Galerkin formulation, and if you compare that with least square, strong formulation is really just least square. That's why usually we don't like least square. I mean, we usually try to avoid least square because it's got worse accuracy. The condition number is much worse.
Okay, thank you. And then you said you couldn't really do much with the weak formulation, and in terms of neural networks. Could you perhaps say what the biggest problem was?
Well, it just got stuck. It's difficult to converge.
Okay. Okay.
Your trial function, you have to sort of update your trial function. It's a bit like GAN. If you know about GAN, you know, the generative adversarial network. It's got the the adversary is like a test function. So you kind of got stuck.
Okay. Thank you.
Just like GAN.
And another question, if I may.
Oh, yes, please.
In the very beginning, when you talked about control problems, you said that control is, for various reasons, preferable to deterministic control. Is there a connection to regularization by noise when you have PDEs or ODEs? PDEs, they may be unstable, but if you add noise, they become stable.
That could very well be the case. The deterministic control, you got stuck much easier than the stochastic control. That, you know, it could very well be it's because of the noise that regularized the thing. Yes, I would say so.
Okay. Thank you. Then the last question, if I may again.
Sure.
It's a very vague one. When you had your picture of this neural network with different layers and states underneath, you had it on a few occasions, I believe. It somehow looked to me a little bit like hidden Markov models, where you have a Markov chain and then an underlying chain of state. Is there any connection, or is it just an optical?
Sorry, I didn't get the most important part. What it's like? What?
Yeah, so here you have, perhaps, maybe I'm wrong, but perhaps you have some sort of a Markov chain structure where each network receives information from the previous one, and as you move through the networks, you only depend on the previous step. And then you have the states underneath, so it looks to me a little bit like hidden Markov models, which have sort of a similar structure, perhaps. But I was wondering if there is any real connection, or if it's just an optical connection.
That's an interesting suggestion. That's an interesting suggestion. I have to think about it. I cannot reply right away. I mean, I think that's an interesting suggestion. Certainly an interesting suggestion.
Thank you very much.
Let me just say to the audience who's following this on Zoom, if you have questions, please indicate that in the chat, and I will read it up, and you can also ask yourself. Are there other questions here? I have one question regarding the issues of boundary conditions. So you had several equations here for which the solution live on an unbounded domain, which is typically a delicate, either to make sure that you have a reasonable error, either by truncating your error, or you're truncating your domain, or trying to solve in the big domain, but to understand the error. I'm wondering, will the flexibility of the neural network, is that something that can help us to solve problems on unbounded domains? And do you have any insight on that?
I would say so. That the neural networks seem to be much more suited for unbounded domains. As a matter of fact, bounded domains make things harder. Unbounded, because we have a formula for the solution, right? We have a formula. We have a function that's defined everywhere. So that helps. In usual finite difference or finite element, you have a grid, and so you have to, it's difficult to put down a grid that goes to infinity. So that makes things harder. Whereas here we have a function defined everywhere, so that makes things a lot easier. Yes.
So I would think that the Schrödinger problem that you suggested would be a great example to show this. But there's another thing that I'm interested in, because you mentioned the issue of regularities, and if you go for high dimension, the classical spaces are not really capturing what we want to do when analyzing these problems. So for the quantum case, then for the standard linear Schrödinger operator, the actual solution makes sense even for just an L2 initial state. So I'm wondering, is this something that we can see in practice? Because if I do my standard finite difference in Schrödinger, I will see if I have something which has less smoothness in the initial conditions, that I'm going to struggle with convergence. Is it possible to see the potential benefit of using neural networks here on a problem for which we can know the solution and see that you will get sort of faster convergence. I understand that you can't analyze the convergence, but that you get better results on more rough functions.
That's also a good question. No, we didn't try. The only people who tried this would be us, and try to solve continuous Schrodinger equations in time-independent Schrodinger equations, but we didn't look at this point. We can go back and look at it. Khalil and Troyer, they were solving discrete Schrodinger equations, so there's no regularity issue there.
Right.
And then most of everybody else was solving stationary ground states.
Right. Yeah. So. So my gut feeling is that the really key or difficult problems in doing this for the Schrodinger is the unbounded domain issue and having non-smooth initial state. And if what you're suggesting is that the neural network can essentially solve both of these things at the same time, that sounds very promising.
The first unbounded domain, that seemed to be quite promising, but regularity in use, I'm not sure. So,
okay.
At least I don't have a good intuition.
I see. Okay, then other questions? I think we should thank Professor again for a wonderful series of talks, and thanks so much.